Cassini-Huygens began as a transatlantic pact between NASA, the European Space Agency, and the Italian Space Agency, a brass-bound alliance built to probe Saturn and its moons. The mission launched from Cape Canaveral Air Force Station, Florida, on October 15, 1997, atop a Titan I-4B Centaur rocket. It was a precise beginning to an odyssey that ended with Saturn orbit insertion on July 1, 2004, delivery of ESA's Huygens probe to Titan on January 14, 2005, and a planned controlled plunge into Saturn on September 15, 2017. From the start, the stakes were clear. 2 vehicles operating as one, decades of uninterrupted power, and a navigation ballet across the inner solar system to pick up speed and aim. Engineers built redundancy into the spacecraft and relied on radioisotope thermoelectric generators powered by plutonium-238 to supply steady watts for years when solar panels were impractical at roughly 9.5 astronomical units. The flight path depended on gravity assists, 2 clever Venus encounters, a single Earth swing-by, and a Jupiter flyby between 1998 and 2000. Each maneuver was timed to the minute to conserve fuel and set the arrival window at Saturn. Deep space communications added another constraint. One-way light time at Saturn was about an hour and a quarter, so guidance, fault protection, and instrument sequencing all had to work autonomously. Twin spacecraft choreography magnified the complexity. Cassini had to carry, protect, deploy, and later relay data from ESA's Huygens probe while maintaining its own instruments and executing orbital insertion burns. Planetary protection rules shaped every contingency. Mission planners avoided any plausible contamination of Saturn's potentially habitable moons, a policy that ultimately dictated Cassini's fiery finale. Programmatic pressures were constant. Budget boards in Washington, facilities and flight teams at JPL, and instrument groups across Europe and Italy pushed schedule and scope into a compact silhouette. This is the practical stagecraft and exacting peril that set the scene. What follows will unpack the engineering gambits, the split-second choices, and the discoveries that made the risk worthwhile. The flight from Cape Canaveral played out like a precise dance of gravity and timing. Cassini used 2 Venus gravity assists on April 26, 1998 and June 24, 1999, an Earth swing-by on August 18, 1999, and a Jupiter flyby on December 30, 2000, to harvest orbital energy and set a course for Saturn. Each encounter was plotted to the minute by navigators at JPL and executed with deep space network tracking, optical navigation, and radio science. Any error could have cascaded into fuel-hungry corrections years later. Early in the cruise, the mission faced engineering jolts that tested the team's resolve. Shortly after launch, teams discovered the high-gain antenna would not latch fully, which reduced planned data rates and forced reliance on the medium and low-gain antennas. Engineers rewrote downlink schedules, reprioritized instrument campaigns, and squeezed science into tighter packets. During the cruise, Cassini entered safe mode on occasion, and flight controllers at the Jet Propulsion Laboratory uploaded software patches and refined fault protection parameters to keep the spacecraft healthy across billions of kilometers. The Jupiter flyby on December 30, 2000 was both a slingshot and a rehearsal. Cassini returned crisp images of Jupiter's storm bands and the Galilean moons, practiced high-stakes navigation, and gained about 2.5 kilometers per second of velocity toward the outer solar system. Arrival at Saturn was the mission's make-or-break moment. On July 1st, 2004, Cassini performed a roughly 96-minute main engine burn for Saturn orbit insertion, an operation carried out despite a one-way light time near 1 hour 20 minutes that forced autonomy and preloaded command sequences. Teams at JPL and instrument leads like Carolyn Porco for the Imaging Science subsystem watched telemetry through the Deep Space Network and held their breath as the ringed planet's gravity captured the spacecraft. The insertion succeeded, and the first orbits brought immediate surprises. En route, on June 11, 2004, Cassini skimmed Phoebe at about 2,068 kilometers, revealing a battered retrograde moon pocked with dark, carbon-rich material and volatile ices, strong evidence it likely originated in the outer solar system. Close passes of Saturn produced images of ring structure far more intricate than the Voyager snapshots. Razor-thin ringlets, braids, clumping, and ephemeral spokes that suggested electrostatic levitation and rapid dynamical processes. Even before the planned Huygens delivery, Cassini's early encounters showed moons that were not just inert rocks, but diverse active worlds, and rings that behaved like living systems. Subscribe. Maybe it will help us eavesdrop on the rings. Those first revelations shattered conservative expectations, refocused the scientific agenda, and set a fevered pace for the investigations to come. The pivot came fast and luminous. On January 14, 2005, ESA's Huygens probe descended through Titan's opaque, nitrogen-rich shroud and touched down on an alien shore, transforming Cassini from a distant surveyor into an excavator of habitability. Huygens, designed and built by European teams with major contributions from the Italian Space Agency, carried the Descent Imager/Spectral Radiometer, DISR, and the Huygens Atmospheric Structure Instrument, HASI. Those instruments recorded pressure, temperature, and startling visual evidence as the probe fell. During the descent, Huygens streamed data to Cassini, and the DISR images revealed river channels, rounded pebbles, and drainage patterns, clear signs that liquids had flowed across surfaces of hydrocarbon sand. On landing, Huygens photographed a damp, pebbled plain and measured methane humidity and complex organic aerosols in the atmosphere. The scene was unmistakable proof that Titan hosts active prebiotic chemistry and surface processes driven by methane and ethane rather than water. Cassini followed up with its own suite of instruments. Radar mapping revealed vast equatorial dune seas and the discovery of polar lakes and seas, including Kraken Mare and Ligeia Mare in 2006 through 2007, confirmed substantial liquid reservoirs on Titan. Those revelations recast Titan from a curiosity into a laboratory for complex organic chemistry and shifted Cassini's priorities toward targeted follow-up measurements of organics, methane cycles, and potential prebiotic niches. The tone shifted again when Cassini turned to Enceladus. In 2005, the Imaging Science Subsystem and magnetometer teams identified dramatic jets erupting from fissures in the Moon's south polar tiger stripe terrain. Those plumes propelled ice grains and vapor into space and seeded Saturn's E-ring. Subsequent flybys sampled the plume directly. Between 2008 and 2009, the Cosmic Dust Analyzer found sodium-rich ice grains, linking the plume to a subsurface salty reservoir, and later analyses by the INMS and CDA detected water vapor, simple organics, and other volatiles. In 2015, Cassini detected molecular hydrogen in the plume gas, a result published later that implied active hydrothermal chemistry capable of providing chemical energy for microbial life. Parallel findings changed how scientists thought about Saturn's rings as well. Instruments detected ring-derived oxygen and charged particle interactions, and showed that ring material constantly rains into Saturn's upper atmosphere, an unexpected chemical coupling between planet and rings. These combined discoveries forced a reorientation. Mission managers at JPL secured extended missions, the Equinox extension beginning in 2008, and the Solstice extension through 2017, and instrument teams reprioritized observing plans to probe habitability. Scientific excitement swelled into urgency, and the ethical stakes rose in tandem. Planetary protection considerations, now squarely focused on preventing biological contamination of Titan and Enceladus, began to shape the choices that would ultimately close Cassini's Gilded chapter. During the Equinox extended mission, 2008 to 2010, and the Solstice extension, 2010 to 2017, Cassini settled into a steady, brass-bound persistence, probing seasonal shifts and magnetospheric drama with scholarly rigor. Around Saturn's equinox in August 2009, sunlight flattened the rings and revealed vertical structures, transient spokes, and unexpected shadowing, details only long-duration observation could catch. Those measurements tracked the faint, aurora-sparkled choreography of particles and plasma across months and years. Instrument teams at the Jet Propulsion Laboratory in Pasadena and across Europe tuned observing campaigns. Radar kept mapping Titan's lakes and dune seas. The composite infrared spectrometer and the ultraviolet imaging spectrograph traced thermal tides and compositional shifts. The magnetometer and the Cassini plasma spectrometer monitored changing fields and charged particle injections as Saturn's seasons marched toward the 2017 solstice. The spacecraft's hardware showed its age. Radioisotope thermoelectric generator output declined predictably as plutonium-238 decayed, forcing instrument duty cycles to be thrifted. Reaction control propellant and hydrazine reserves thinned after thousands of maneuvers, and intermittent anomalies demanded conservative margins. Deep Space Network contacts at Goldstone, Madrid, and Canberra became windows to ration power and rehearse complex sequences days in advance, each contact balanced in a ledger of watts and grams of fuel. Discovery pressure mounted as Enceladus's hydrothermal plume chemistry and Titan's methane cycle suggested astrobiological promise. Scientists, led publicly by project scientist Linda Spilker and imaging lead Carolyn Porco, urged ambitious encounters. Mission managers at NASA and JPL faced a ledger rendered in hard choices. Continue expensive, fuel-consuming close passes to chase every tantalizing clue, or conserve resources to meet planetary protection obligations under NASA policy and international COSPAR guidance. The ethical weight was not abstract. Enceladus's subsurface ocean and Titan's organic-rich surface are environments where Earth microbes, if accidentally delivered, could confound future life detection efforts. That reality converted programmatic arithmetic into an existential imperative. Cassini could not be allowed to risk forward contamination. In boardrooms and operations rooms, the debate tightened into a clear fork. Engineers modeled fuel budgets and failure modes. Scientists modeled lost opportunities for plume sampling or high-resolution ring science. Lawyers and planetary protection officers enumerated constraints. The chosen path stitched science and safeguard together, a concentrated final act of ring grazing and grand finale orbits that would sample previously inaccessible regions between the innermost rings and Saturn's atmosphere while reserving enough propellant to execute a commanded, controlled plunge into Saturn. The decision set a deadline and focused every remaining watt and maneuver on extracting maximal, irreplaceable data before the crucible of re-entry, building inexorably toward the mission's climax. The grand finale narrowed into a daring, brass-bound sequence of 22 proximal orbits between April and September 2017 that threaded Cassini through the narrow, sepia-hued corridor separating Saturn's innermost rings from its cloud tops. Navigators at JPL choreographed each pass with clockwork precision, and the Deep Space Network stations in Goldstone, Madrid, and Canberra relayed up-to-the-minute telemetry as engineers tuned attitude control and propulsive trims to fractions of a degree. The gambit let instruments that had watched from afar finally sample the unseen. INMS, ion and neutral mass spectrometer, tasted tenuous gases at the ring atmosphere interface. CDA, cosmic dust analyzer, counted dust and icy grains raining from the rings. MAG, magnetometer, and RPWS, radio and plasma wave science, mapped magnetic and plasma currents inside the ring plane, and RSS, radio science subsystem, and gravity experiments refined Saturn's interior profile and ring mass to an unprecedented precision. Those close brushes exposed processes impossible to infer from distance. Ring material streaming into the atmosphere as ring rain, subtle gravitational gradients revealing ring mass and age, and charged particle dynamics that braided the planet and its rings into a single living system. Each orbit extracted irreplaceable data, Each downlink arrived like a gilded ledger of discovery. The final chapter was deliberate and sorrowful, with hydrazine and power dwindling, and because of planetary protection obligations, especially for Enceladus and Titan, project manager Earl Mays, project scientist Linda Spilker, and imaging lead Carolyn Porco concurred on a controlled end. On September 15, 2017, Cassini executed a commanded deorbit and plunged into Saturn, transmitting its last packet of data back to Earth before radio silence. The end of the signal sealed both scientific triumph and the fulfillment of an ethical duty. Cassini sacrificed itself to preserve future astrobiology, leaving a trove of proximal measurements that would begin to rewrite our understanding of the ringed world. After its final plunge into Saturn on September 15, 2017, Cassini's legacy settled across planetary science like a brass ledger. The mission turned Titan and Enceladus from curiosities into working laboratories for prebiotic chemistry and habitable oceans. Huygens' descent on January 14, 2005 imaged fluvial channels and a methane-shrouded surface on Titan, while Cassini's analysis of Enceladus's plumes, culminating in the detection of molecular hydrogen, established active hydrothermal processes and made icy moons prime targets in the search for life. Ring science was transformed by the grand finale. Gravity measurements and in situ sampling that quantified ring mass revealed ring rain and tied ring evolution to planetary atmospheres. Those discoveries changed NASA and international planetary protection practice, tightening end-of-mission disposal rules and shaping plans for follow-on explorers like Europa Clipper and Dragonfly. Cassini also left an immense archive in NASA's planetary data system, a trove of images, spectra, and particle data that will drive research for decades. Engineering lessons in long-duration autonomy, radioisotope thermoelectric generators, RTGs, and power management, deep space navigation, and fault protection are now templates for missions beyond the frost line. Culturally, Cassini burned powerful images into the public imagination, sparking outreach and a sense of wonder. Its final act preserved the chance of future discovery. The question it leaves us with is simple and austere. What will we find next?